All right, this video is over section 5.3, functions and relations. A relation is really a set of ordered pairs. So really just two numbers that have some kind of connection. X, Y typically could be a lot of different things. So basically two things that have some kind of connection. Um, the domain is the set of all X values. The range is the set of all Y values. And some synonyms or other words you'll see is would be domain is like input, so range would be output. Yeah. Domain X, range Y, input, output. You'll see those interchangeably. A function is a relation. So given a relation, in X and Y, we say that Y is a function of X if for each value of X in the domain, there is exactly one Y value in the range. Sorry, that really came out from the box, but every X value has one Y value. All right, so for these first few, it says determine if the relation defines Y as a function of X. So here we've got 4, 3, 2, -1, and 2, 5. So basically, I'll use a different color, but basically a function means that X is not repeating. And I'm using orange because it's not super mathy to say that, but we don't want multiple X's. If we have multiple X's, then we're going to have not a function. All right, so here we have X is 4, X is 2, and X is 2. So because this one would be not a function, and that's because 2, well, I guess I'll say X equals 2, because X equals 2, I'll say goes to multiple Y values. So you can see above that 2 goes to -1 and 2 goes to 15. That's not going to be a function. For the second one, we have 5, -12, 3, -12, 4, 14, and 10, 1. So 5, 3, 4, and 10 are our input values. There's no repeating. So this one is going to be a function. And I'll say because every X value goes to one Y value. And if you notice here, Y does repeat, so we've got -12 and -12. That's okay. Y is allowed to repeat. We do not want X to be mapped to two different Y values. All right, for this W graph, if you notice here, we have like X is equal to -12. There's no other place on this W. Let me change that color real quick so we can see it better. Let me make that orange. So if we see that X equals -12 where I drew that line, there's no other place on the graph where X is also equal to -12. So this one is also a function. And that's just because every X value has only one Y value. So any X that you pick on that W, we could pick like this X right here. If I draw up and down line, there's no other place where that W hits X equals, I guess that's about 10. However, for this circle, if I picked like x equals -2, on that circle, there's that dot that I just drew is at -2, but also this dot down here is also at -2. So this is not a function. And really, you just have to give one example of it not being a function. But there's like an infinite number of examples here. Um, but if you just gave that one example, that would be sufficient. I'm not going to write it because I think we understand the gist of how to write it. But basically, what we're saying is that this one x value has multiple y values. So a little bit clearer would be like x equals 0 is right here. So if I look at my circle graph, we have x equals 0, 3. So I wrote that as a point, 0, 3. Down here, if I wrote that as a point, 0, -3. So that 0 is repeating. 0 goes to two different x values. So this circle is not a function. All right, this last, or this box right here, this is called a mapping diagram. So let me just label that so you can add that to your vocabulary if you don't already know that. And we're still looking for that same thing. We don't want x to repeat. So here, if you look at one goes to A and one goes to B. So that would be a counter example. So this would be not a function. And that's because one goes to A and one goes to B. And kind of how you can think about it is if I write that as an ordered pair, 1A and 1B, that 1 for X is repeating. It doesn't look like ordered pairs, but this mapping diagram is just a weird way to show ordered pairs. All right, next we have a couple of equations. So I have the absolute value of y minus 1 equals x. And what we're trying to do is we're trying to figure out if I put in an x here and a y here, I want to see if I can think of two different x's that would give me the same y value. Okay, so if I chose, let's say x equals 5. And if I did 6 minus 1 absolute value, that would be absolute value of 5, which would be 5. However, if I did, let's see, -4 minus 1, that would also be, or that would be -5, which would give me an absolute value of 5 as well. So this is not a function. And that is because, and notice here, it's kind of weird because we were picking y values, but we're getting this same x value. So that is x right there. And that's because I have the points 5, 6, and I have the point 5, -4. So because I was able to come up with an example where my x repeated, this would not be a function. All right, for this next one, we have x squared plus y squared equals 16. Now we skipped the previous section in this book, so if you're following along in the book, section 5.2 is over circles. So if you followed that, then you would know that this is an equation for a circle. Up here you can see circles are not functions, so we already know this is not a function because it's a circle. So again, let's try to find an example of x where we keep x the same, but we have two different y values that equal 16. So if I choose x is equal to 4, let's not do 4. Let's choose x equal to 2. Then I could have 2 squared plus y squared is equal to 16. Oops, let's just change out that x for a 2. And if I have that, I have 4 plus y squared is equal to 16. And if I solve this, I'm going to have y squared is equal to 12, and y would be equal to plus or minus the square root of 12, which we could reduce and simplify, but either way we have this plus or minus here. So we have two different y values with x equals 2, so this would make this one not a function. And again, if you graphed it, it would make a circle. Awesome. On the next page, it just says evaluate the function defined by h of x equals 5x minus 2 for the given value of x. Evaluate is the easiest kind of algebra where you're just plugging in. So for h of -3, we are plugging in 5 times -3 minus 2, which would be -15 minus 2, which would give us -17. And that's it. H of 0, we have 5 times 0 minus 2, which would be 0 minus 2, which would just be -2. H of -1, we have 5 times -1 minus 2, which is -5 minus 2, which is -7. h of 1, 5 times 1 minus 2, which would be 5 minus 2, which would be 3. So that section is just plugging in values for x. The next one says evaluate the function defined by f of x equals negative 2x squared minus 4x for the given values of x. So for this first one, we have f of t. So all we're going to be doing is replacing, let me zoom in, replacing x and x with t's. So it's going to be so easy. It's a little bit confusing, but we're replacing those x's. So I'm going to have negative 2. Instead of x, I'm going to have t squared minus 4. And instead of x, I'm going to have t. And that's it. Literally, that's it. Nothing to plug in. They didn't give us a number. They just said plug in t. For this next one, we are plugging in a plus h for those pink highlights or those x's. So this one's just as easy, just a couple more steps. So we're going to have negative 2 parentheses a plus h squared minus 4 times a plus h. This is totally fine to leave here. I am worried that like on a multiple choice or on an online assignment or something that it would want you to simplify. So we're going to go ahead and simplify. If it was a written assignment, I would take this, but I'm not sure that they will let you. So in order to simplify, if I multiply this out, a plus h squared, I'll go over here and do that. That would be a plus h times a plus h, which would be a squared plus ah plus h squared, which would be a squared plus 2ah plus h squared, which is just perfect, what's it called? There's a special word for it, but basically this is just like a rule we follow when we square something. Perfect square, I guess. So this would be a squared plus 2ah plus h squared. And then for the second parentheses, we distribute that 4, so minus 4a plus, I guess, minus, again, 4h. For the first parentheses, distribute that negative 2, so negative 2a squared minus 4ah minus 2h squared minus 4a minus 4h. I thought there might be like terms, but there's really not. Like these have ah, but that one's ah together, so those are not like terms. So really there's nothing else to do. All right, next, find the x and y intercepts of the function defined by f of x equals the absolute value of x minus 3. When we're looking for the x-intercepts, that's where we cross the x-axis. And when we cross the x-axis, we have our y is equal to 0. Same thing with y-intercepts, that's where we cross the y-axis. And when we cross the y-axis, our x is equal to 0. So y-intercepts are actually a little bit easier because we're just plugging in 0. So for this, we'll have y equals the absolute value of 0 minus 3. So this would be y equals 0 minus 3. So for us, this y-intercept would be x equals 0, y is equal to negative 3. Now for the x-intercepts, it's a little more complicated because there's usually 2 of them, but we're going to plug in 0 for the y. So I'm going to try to write small. We're going to have 0 equals the absolute value of x minus 3, and we're going to try to solve for x. So if I add 3 to both sides, I'm going to have 3 equals the absolute value of x. And if I solve that, we're going to get two answers, 3 and negative 3. So this one has two x-intercepts at 3, 0, and then it has another x-intercept at negative 3, 0. Next says determine the domain and range for the function below. And remember, domain is x values. So it gives us those 3 points. We need to list out the x values. Typically, you list them smallest to biggest. So if we do that, we would have negative 2, 1.5, and 2. Those are the 3 x values for those 3 dots. Next, range would be the y values. Again, we go smallest to biggest. You don't need to have them line up with their counterparts there. Not necessary. So the smallest y would be negative 1, then positive 1, then 3. Next one, domain here. If we used interval notation, then notice here on the left, we go forever to the left. So all of these x values are going to be hit forever and ever and ever and ever to the left. So the smallest x value ever would be negative infinity. And similarly, because of this arrow, it's pointing to the right forever and ever and ever and ever. So the right would be positive infinity. We always put curved brackets around infinity. Next, we have range. Here, the range actually stops at 0. It does not go below 0. So our smallest y value would be 0. And then there's two different sides for pointing up, but luckily they're pointing the same direction, up. And so the biggest y value ever would be infinity. You can never get there, so we have a curved bracket. We are going to include 0 because there is a really small but filled in dot at 0. Next section, write the domain of each function in the interval notation. Now we could graph these and then kind of see. On your calculator, it's not going to be a perfect graph, and even if you use desmos.com, so you could graph in TI-84 or desmos.com. It's not always going to graph these perfectly. It often will, and on these maybe it would, but I think you're going to miss out if you don't totally understand how the equations work. So for this first one, it's a rational equation, and when we have a rational equation, we know we can't divide by 0. So in order to write, you cannot divide by 0. So that's going to be a huge help for us when we're thinking about domain and range. So if we cannot divide by 0, we know that x minus 3 cannot be 0. So that means that x cannot be 3. If I were to add 3 to both sides, we know that x cannot be 3. So therefore, our domain is going to be any number but 3. So if I take a gap at 3, I'm going to go negative infinity to 3, union, which is going to kind of be like my gap, 3 to positive infinity. So what this says is that the domain is any number not 3. We know not 3 because these are curved brackets, not square brackets. All right, for this one next to the side, same concept. We have a rational equation where we divide. And so because we cannot divide by 0, we know 3x plus 1 cannot be 0. I'm not going to show more because the box is so tiny. So we know that 3x cannot be negative 1 because we subtracted 1. And thus we know that x cannot be negative 1/3 because we divided by 3. So for this one, the domain is going to be very similar to the last one. We're going to have a gap this time at negative 1/3. So this would be negative infinity to negative 1/3 with my gap or union with the next section, negative 1/3 all the way to positive infinity. So there's a tiny, 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 tiny infinitesimal gap at negative 1/3. Cannot equal negative 1/3. All right, this next one we are dividing by 12, which there's no x in it, so it really has no factor on this. So this one, the domain for this one is just all real numbers. I think that that will be an option online, but the other way to write all real numbers with infinities would be just negative infinity to infinity. There's no gap on this one, 12's on the bottom. There's no x, so x isn't really a factor because this x word on top is always continuous. K of x, 3 divided by x squared minus 2x minus 15. We need to factor the denominator, so we're going to have x and x. And when I factor this, I'm going to get negative 5 and plus 3. So we know x minus 5 cannot be 0, and x plus 3 cannot be 0, because we cannot have anything in the 0 in the denominator. And if either one of those were to happen, we would. And so we know x cannot be 5, and we know x cannot be negative 3. So when we write the domain, we have two gaps. So we're going to go from negative infinity to negative 3. We're going to have a gap at negative 3 and then another gap at 5. So this next little section in our graph is going to go to 5, and then that will connect 5 to infinity. So we have two gaps at negative 3 and 5. Last one, we have square root of x minus 6, and we know that cannot be 0 because it's in the denominator. We also know that if we're taking the square root of something, we know this has to be actually greater than 0. So I could solve it like this to get my direct answer, but we also know it needs to be greater than 0. So I'm trying to think ahead. I think that it's going to give us the same answer if we just solve this one. So that would mean x minus 6 must be greater than 0, and that means that x must be greater than 6. If it's smaller than 6, then we would have a negative under our square root, and that would not be okay. So when we write our domain for this, we are going from 6 to infinity. No gaps. We just don't start till 6. Last one, 3x squared minus 8x. There's no denominator. There's no square roots. There's really no restrictions on this equation. So our domain is just all real numbers or negative infinity to infinity. All right, last section, we're looking at this function pictured, and we are going to fill in the blanks. So it says determine f of -2, which means x is -2. For that, we have y equals 2. F of -5 would be what y is at x equals -5, which would be 0. Find all x for which f of x is equal to 0. So let me erase our dots so we can see a little better. That means y is equal to 0, and if I draw this horizontal line here, we see it happens 3 times, once at -5, once at -1, and once at +4. So we have 3 answers there. Next question says find all x for which f of x is equal to 3. So same thing. Taking our f of x equal to 3, that one happens once. It looks like it's a little past 5, so I'm going to just say about 5.2. Right there. Determine all x-intercepts, so that's where it crosses the x-axis. We already did that. It's that line right there. We already did it, so same answer from literally right above it. There are 3 x-intercepts, one at -5, one at -1, and one at 4. Determine the y-intercept. There's only one. It looks like it's a little bit above -2, so let's say just -1.8. The domain, we're going to assume that these kind of like are arrows going off the page, so we'll just assume our domain is all real numbers. It goes left and right forever, and then same with the range, up and down forever. If you wanted to write this y-intercept as a point, you could write 0, -1.8, and then same with these could also be written as a point. I just didn't give myself the space.